So hopefully reaction mechanism 13 is not unlucky, and it's actually one of the easiest mechanisms for you to do thus far, because this is another one of these mechanisms where we're simply replacing a hydrogen with an R group compared to reaction mechanism 12. So in this case, rather than starting with a hemiacetal, we're going to be starting with a hemiketal. So again, a hemiketal is going to have an ether connection to a carbon attached to two other carbons, and then an OH group. So with so many of these mechanisms, if there's something that we don't want to be part of our molecule anymore, we're going to protonate it to make it a good leaving group. And now we've got this wonderful internal lone pair of electrons on an adjacent heteroatom, in this case an alcohol, that can allow us to push out that leaving group, have it depart. We're left with a protonated ketone and departure of our alcohol. And then we can deprotonate this protonated ketone to generate our final product here. Final ketone. So pretty simple mechanism here. So as a way to kind of add some additional content to this video, I wanted to take a moment and sort of highlight, since we're pretty much halfway through our mechanisms, what we've sort of done in the first half of our mechanism series, right? So again, an important thing to remember is when you're studying mechanisms for quizzes, because you're not going to see these exact mechanisms, it's not really useful to memorize these exact mechanisms. Rather, look for themes, understand how molecules react, right? The thought is that you're never going to, try to memorize a certain number of mechanisms, right? That volume of knowledge is just going to get bigger and bigger and bigger, and then you really don't know how to apply it to a new system, which is really the kind of question you're going to see on an exam. I'm going to show you a mechanism that you haven't seen before, and I'm going to have you try to sort out how to do it. So recognizing those patterns or kind of types of reactivity is going to be what's really important. So what I'm going to do for the last part of this video here, and kind of to sum up the first half of the reaction mechanisms that we've done, is kind of highlight that we've really only done 3 kinds of mechanisms thus far. So we're going to kind of summarize what they are, and hopefully, since you've done them already, it'll be an opportunity for you to kind of see that information together. So the first reaction mechanisms that we did, reaction mechanisms 1 through 3, were chemistry between amines and carbonyl containing compounds. Now in this case, we're really, the first mechanism was actually not to make an amide bond, which is what everybody wanted to do. But again, recognizing the theme we have is when we have a carboxylic acid, we really have acid-base chemistry. When we have acid anhydrides, we do finally have that chemically activated carbonyl-containing compound, that carboxylate, so that we can do that chemical activation, or we can do that coupling chemistry to generate the amide that we're interested in. But the most relevant, and the one I've kind of listed below, I just copied and pasted it from reaction mechanism 3, was sort of this biological activation. And again, remember, we wanted to do chemistry where we started out with a carboxylic acid, and we couldn't do chemistry there because that hydrogen atom that we had there was also a good electrophile. So in this case, we're going to have our carbonyl containing compound now with a good leaving group. Now our amine can act as a nucleophile rather than a base. Nucleophilic attack, kind of a theme that we're going to see here, is carbonyl containing compounds. When we have a good nucleophile, nucleophilic attack generates a tetrahedral intermediate. Common theme that we're going to see is sort of a proton rearrangement. So we have something that was previously a good leaving group that's going to no longer be a good leaving group. And then we're going to protonate up here, departure of our good leaving group, and again, deprotonation of our final product gives us to the amide that we tried to make in reaction mechanism 1, but we couldn't do until we got rid of that proton. Because remember, anything that's a good nucleophile is also going to be a good base. So we have to watch out for protonated or molecules that are acidic, because that can get in the way of things. So that was reaction mechanisms 1 through 3. Reaction mechanisms 4 through 7, and then the ones that we just finished, 10 through 13, are actually all related. They're chemistry between alcohols and carbonyl compounds, those that have poor leaving groups, like we see with ketones and aldehydes. So again, we're going to still form that tetrahedral intermediate, but in not having a good leaving group, we're basically going to only have the option to protonate and generate our final product. So the purpose of this was it allowed us to essentially protect our reactive carbonyl group. So reaction mechanisms 4 through 7 were really kind of generating those protonated intermediates, or I'm sorry, those protected intermediates to protect that functional group. So again, we start with a carbonyl as either an aldehyde or a ketone. We go to the hemi flavor. So I've actually only shown these mechanisms with sort of the ketone version. So again, reactive functional group is in a ketone. We use one equivalent of alcohol to generate our hemiketal. And then our second equivalent of alcohol here with our hemiketal could generate our ketal. So again, what we've done is protect this carbonyl functional group, which is fairly reactive. And then the last series really was reversing these reactions. So reaction mechanisms 10 through 13, we're taking ketals and then converting them back into hemiketals. And then the last mechanism that we just did, so again, just to highlight that this is reaction mechanism 13, so the one we just did would kind of go into this space here. That's kind of taking that hemiketal and walking it back to the ketone. So 4 mechanisms here just to deal with the ketone flavor, 4 to deal with the aldehyde flavor. That's how we get these 8 related reaction mechanisms. So why do we spend so much time just on these reaction mechanisms? This has a lot to do with sugar biochemistry. So kind of whether it's sugar cyclization when we have our hemi flavors, or sugar polymerization in the formation of glycosidic bonds when we form our ketal and our acetal flavors. So again, this is important because this is nature's way of protecting the reactive aldehyde and ketone functional groups that we see in sugars and allowing us to polymerize these sugars for storage. So we're going to revisit these reaction mechanisms quite a bit as we begin to understand sugar metabolism. So a set of reaction mechanisms that sort of came in the middle of all that is reaction mechanisms 8 and 9. And again, this is probably the first set that maybe kind of made you question about what's going on. And again, with good reason, we switched kinds of chemistry that we were doing. We weren't looking at chemistry at the carbonyl carbon. Rather, again, the carbonyl carbon is important because it serves as a mechanism for stabilizing the enolate that we're going to generate by deprotonating the alpha carbon, the adjacent alpha carbon. So again, themes that we see sort of for this is we can actually interchange ketones and aldehydes when we have this requisite functional group, a hydroxyl on the alpha carbon. So just kind of reminding ourselves here, because this is going to become important, just as a little preview, reaction mechanism 14 begins with something that looks similar to this, okay? But one of the things that's going to be different is it is not containing this OH group on the alpha carbon. But the alpha carbon's atom hydrogen atom, the alpha carbon's hydrogen atom is acidic because the resultant carbanion that we generate can be resonance stabilized by putting that negative charge on the oxygen. And so this enolate intermediate allows for sufficient stability of that deprotonated species. And remember, if you want to ask the question, is a molecule acidic? Deprotonate it, take off that hydrogen atom, look at the resultant conjugate base and ask if there's a mechanism for stabilizing it. If you can stabilize it, that means you're going to decrease your pKa. You're going to make it more acidic. So again, we walked between an alpha hydroxy aldehyde to an alpha hydroxy ketone, doing the mechanism shown here. And then the reversal was reaction mechanism 9, where we basically just walked it back the other way. So starting from an alpha hydroxy ketone, going back to an alpha hydroxy aldehyde.